Alright, let's start delving into actual circular motion using Newton's law. So before we get to that though, we have to kind of lay some foundational work again. So we're going to start to talk about these terms called period and frequency. So I'm going to use the example, let's say you throw a baseball. You're kind of on the pitcher's mound and you throw a baseball from the pitcher's mound to home plate. And let's say you throw it at about 160 kilometers per hour. So if we took a camera and kind of recorded that ball's motion, we're going to see two things. First of all, we're going to see the ball actually going from the pitcher's mound to home plate. So like if we kind of drew this scenario, like here's the pitcher here, they're going to throw the ball, and they're going to throw it to home plate here. Now, we could record a velocity for this. This velocity is what we call the translational velocity. That's the velocity, that's basically looking at the displacement, the linear displacement, like getting from point A to point B, or from from the pitcher's mound to home plate. Translational velocity is what we've been calling just velocity this whole time. But if you also look at this in slow motion, you'll probably also notice that the ball, it just doesn't move, it just doesn't translate, but you're also going to notice that the ball is going to rotate about its axis. So that also is going to incorporate rotational velocity, which is a measure of how fast this ball is going to rotate about its axis. And it can have both of these motions simultaneously. So you'll have that translational velocity getting from the pitcher's mound to home plate, the standard velocity we've been dealing with the whole time. But it's also going to have that rotational velocity associated with it. Now, we won't be looking at the rotational velocity per se in Physics 20, but we are going to look at some other things. And some of the terms that come up, we're going to need them now, but you're going to need them a little bit later too in the course when we start to do some of the wave mechanics. So the first term that's going to come up is going to be this term revolution. So a revolution represents a complete cycle. In circular motion, it basically represents one complete tracing of a circular orbit. So for example, and again, apologies for my drawings. So let's say I have the sun here. It's going to be in pink. And then, I got the Earth here, and it's going to do its orbit around the sun. So that one complete orbit here, we would call that one revolution. So one revolution basically means one full circle. Now, the other part with that revolution is sometimes we might not be interested in the actual distance, like this whole distance around for one revolution. We might be interested in the time it takes for that. So we know for the Earth going around the sun, we know that the time of that revolution is about 365 days or 1 year. And, if we look at a seconds hands on a watch as it's ticking around, it's going to take 60 seconds to get around. We'd say that that is the time for that complete revolution. But that time frame, or that time specifically for one revolution to happen, this is what we call the period. Now, very formally, the period is going to be in units of seconds per revolution because we're timing how long it takes for one revolution. But we usually drop the per revolution part, so we're just going to say that the units for period is seconds. Ignore the per revolution part. Now, that's a great thing to know, how long it takes to do one complete revolution. But for things that move really fast, it might be hard to time that. Like that period might be really small. So there's something else that we would want to look at instead. And what we may look at instead of looking at the period, we're going to look at this thing called the frequency. So the frequency basically counts how many revolutions are happening each second. So for example, like if I was, and I'm going to draw myself here. So there's me. Now, let's say I was twirling a yo-yo around my head. And let's say I was able to make 3 complete circles every second. If I said I had 3 revolutions per second, we'd say that that's the frequency. Because again, the frequency is a measure of how many complete revolutions, how many revolutions are we having every single second. So for this, it has a special unit as well. It's this revolutions per second. But just like the period, we don't actually keep the revolutions. So the units for period, the units for frequency are going to be this inverse seconds, or we could say seconds to the -1. But we're not going to use the second to the -1. For frequency, we actually have a very special unit for frequency. It's actually called the Hertz, or the uppercase HZ, named in honor of Heinrich Hertz. So instead of saying my frequency with that yo-yo I rotated above my head, instead of saying 3 revolutions per second, we'd actually say the frequency is 3 hertz. They both mean the same thing. So with that, you may have noticed that the units on period and frequency are similar, but not quite the same. This leads us to a very simple relationship in that the period is equal to 1 over the frequency. So they are inverses of one another. So t is going to be our period in seconds, and then f is going to be the frequency in hertz. Or you could say seconds to the -1, but I'm definitely recommending stick with hertz. Now, with that whole measuring of revolutions per second, those of you that are a little bit more handy, do a lot of work with power tools or even do work with automotives, you've dealt with frequency, but not in the unit of hertz most likely. You've probably dealt with a special unit called revolutions per minute, or RPM. So RPM has a very similar definition. It's just talking about how many revolutions do we have in a minute as opposed to every second. So we could convert between the two. If we have something in hertz and we want to go to RPM, we're going to multiply by 60 seconds for every minute. And then if we want to go from RPM to hertz, we're going to divide by 60 seconds per minute. So just something a little handy. And we'll just look at a very quick example of that. So we get a circular saw. It happens to run at 3,000 revolutions per minute. So we want to determine its frequency in hertz, and we want to determine the period. So to get the period, F has to be in hertz. We can't do the period with the with the frequency in RPMs. We have to have it in hertz. So what I have here is I have 3,000 RPM, but I don't want to write RPM because it's not helpful for unit analysis. So why don't I write it like this, 3,000 revolutions per minute. Now we know that a hertz is just a revolution per second. So what I would like to do is I'd like to get rid of this minutes on the bottom and put seconds there instead. So we need to have something with minutes up top and seconds on the bottom. Well, for simplicity, we know that in 1 minute we're going to have 60 seconds. So if I multiply 3,000 by 1 divided by 60, this should give me my frequency in hertz. So the minutes are going to take care of each other. So I have 3,000 divided by 60. This should be 50, I believe. Yes. So we're going to have 50.00. And then we have that revolutions per second. But like I said, we're not going to do the revolutions per second. We're just going to say that the frequency is 50.00 hertz. So instead of saying that this circular saw, it makes 3,000 revolutions every minute, what we mean by it having a frequency of 50 hertz, we're saying that every single second it does 50 revolutions. So last period, we know period's 1 over frequency, so we're just going to divide 1 by 50. And then for that, we are going to get about 0.02000 seconds. So that covers us for a period. So this is the number of revolutions per second. The period represents the time it takes for 1 complete revolution. So what this is telling us is that in this circular saw, for it to do 1 complete circle, it's going to take 0.02 seconds. So very fast. And we'll use these relationships quite a bit in this unit. We'll definitely use them a lot more when we get to the last bit on wave mechanics.